Hello everyone. So this is the continuation of our lecture series regarding series solutions of ordinary differential equations. And as I've mentioned in our first three parts of our video or lecture series, we have many techniques of solving the general solution. One is by substitution of an exponential ansatz, and the second is by using the Frobenius method. In part 3 of our lecture series, I have introduced the concepts of Frobenius method, wherein we propose a solution that is a power series solution, and then that just substitute it to our ordinary differential equation, find the derivatives, and then substitute it as the case may be. So let's try to apply the concept of Frobenius method to our linear oscillator model, where, as we know, the solution to this problem is a trigonometric function of sine and cosine, and by application of Euler's identity, we found that the solution could also be expressed in terms of an exponential solution. So again, these are the steps that we follow for the application of Frobenius method. We first find the derivatives of the proposed solution. We substitute the derivatives as well as the original power series that we proposed to our ordinary differential equation. In this case, our ODE is the linear oscillator equation. And then the tricky part of the solution, we shift the indices to equate the powers of x and find the initial equations. We then find this so-called recurrence relation. We solve for the coefficients, and just that, we find the general form of the solution. So we start with the first step, that is finding the derivatives of the power series. This is the summation of a lambda x to the k plus lambda, where lambda starts from 0 to infinity. So in this solution, we will actually be looking for the values of k, so that when we expand when we find our general solution, we can we can make use of the values that we found based on the initial equation that we will be solving later in this presentation. So of course, the first derivative of our power series is given by this a lambda times k plus lambda x to the k plus lambda minus 1. We also have the second derivative given by this equation. So of course, we are left with minus 2, no, with the power of x upon getting the second derivative with respect to x. Now, after finding the derivatives, we then substitute the results to our original linear oscillator model. This is our linear oscillator equation. So we have here the second derivative plus omega squared. So that's our omega squared times our power series solution. And then we can directly see that upon expansion of this equation, that is by getting the first term of lambda is equal to 0. Then we have a naught k times k minus 1 times x to the k minus 2 plus this summation, where lambda now starts from 1 to infinity. The reason is because we already solved lambda is equal to 0. And then we have, for the second term, we have plus omega squared a naught x to the k plus the remaining terms in the summation, but in this case, we start from lambda is equal to 1 to infinity. Now, this expansion is very essential for us to be able to look for the values of k, and we can see that by looking into the lowest power of x. In this case, we have the lowest power of x is x to the k minus 2. And we can see that since this is the lowest power of x, no, as x to the k minus 2, then our initial equation for the values of k is this. We have a naught k to k times k minus 1 is equal to 0. And later on, we can see how this works, how this initial equation works. Now, the tricky part actually in the Frobenius method is the cancellation of terms as much as possible, because we want to simplify our equations. And we can see that the powers in the first term and that of the second term are not the same, so we cannot just cancel out x to these powers without running afoul of any mathematical principles. So normally we do shifting of the indices. So to combine the summations, we shift the index of the second term in this case. It's also possible to shift the index of the first term, but I find it more feasible and more practical to just shift the index of the second term. But should you want to, or should you try to shift the first term of our equation, then it's also okay. And this allows us to equate coefficients of the same power of x. We can notice that x now has, for the first and the second term, have the same powers. That is, instead of k plus lambda, we have minus 2 for the first term. Of course, we retain that. And for the second term, instead of x to the k plus lambda, we have k plus lambda minus 2. But notice that since we shifted the index of the second term, our summation now starts from 2 to infinity. No? So instead of starting from 0 to infinity, we started from 2 to infinity. And we did this to have consistency, mathematical consistency, because otherwise we will be violating some mathematical principles. So the initial equations are then a naught times k minus 1 is equal to 0. And we can directly see that the values of k are 0 and 1. And we will be using these cases. We have two cases. One case is for k is equal to 0, and another case is for k is equal to 1. So we will be using these cases for our general solution. Now, the next step is to find the recurrence relation. So for the remaining coefficients of the summation to vanish, we derive a recurrence relation that connects coefficients of different powers of x. That is, instead of k plus lambda, we introduce x to the k plus j, and this must vanish. So the equation now becomes aj plus 2 times k plus j plus 2 times k plus j plus 1 plus omega squared. This is, notice that this is the second term of our previous equation, omega squared times aj is equal to 0, where obviously j is equal to lambda minus 2. Now, if we plug in this, back to our equation, you can notice that we arrive at the same equation as the previous equation. So, by solving aj plus 2, of course, you just have to transpose this to the other side of the equal and then divide both sides by this quantity. So we have aj plus 2 is equal to negative aj times omega squared over k plus j plus 2 times k plus j plus 1. And this relation is crucial for finding the series coefficients. Now the next is to solve for the coefficients. And notice that we have two values for k. We have k is equal to 0 and k is equal to 1. So for this case, we first test k is equal to 0. Notice that this is our recurrence relation. We have aj plus 2 is equal to this. So let's try to consider k is equal to 0 and find what are the values or what are the different equations for aj plus 2 for different values of j. So if j is equal to 0, we notice that this becomes 0. So that's a2 is equal to a0 omega squared k plus 0 plus 2. So that's 0 plus 2. So that's 2. We have 0 plus 0 plus 1. So that's 1. So for j is equal to 0 and k is equal to 0, we have negative a naught or a sub 0 omega squared over, this is just 2 factorial. For j is equal to 1, we have negative a1 omega squared over 3 times 2 times 1, so that's 3 factorial. If j is equal to 2, we have a sub 4 is equal to negative a2 omega squared over 4 times 3. But notice that a sub 2 has already been solved. That's negative a naught times omega squared over 2 factorial. So we arrive with this, and the final answer for j is equal to 2 and k is equal to 0 is a naught times omega to the 4th over 4 factorial. And then finally, for j is equal to 3, we have a5, so that's 3 plus 2, so that's a5, is equal to negative a3 times omega squared over 5 times 4. But notice that we were able to solve a3, that's negative a1 omega squared over 3 factorial. So the final answer for j is equal to 3 is a1 times omega to the 4 over 5 factorial. And we can actually see, no, that for the positive values for a to n, that is for even values as multiples of n, we can see the relation as negative 1 to the n times omega to the n over 2n quantity factorial times a naught. And we will be using this relation to look for our general solution. So that's it for this video. For our next video, we will be solving the general form of coefficients and the solution for our problem by making use of the relation that we have just found in our 5th step, that is a to n is equal to negative 1 quantity to the n times omega to the 2n over the quantity 2n factorial times a naught.